We are actually the largest natural gas distribution utility in the country, right? We cover about 24,000 square miles of terrain. We've adopted all of these very great aggressive clean energy targets. There's, a huge push for decarbonizing our economy, but how we're going to get there, or how we're going to, decarbonize our economy will require essentially a strategy, and we will still need clean fuel specifically to power our economy, whether that's aviation, right? Port complexes, the heavy duty, sector, the mobility sector, heavy industry, and even power generation. The federal government is investing about $7 billion in developing hydrogen hubs. And then also there was some money that was set aside as well for carbon management solutions. So think of carbon capture or direct air capture technologies. And California actually was one of those hubs. So we are slated to receive about $1.2 billion in federal funding to facilitate the development of hydrogen hubs in California. So what is SoCalGas' role in developing this? I think that our hydrogen distribution network is fully developed, and unfortunately it's not. And I think that's one of the biggest reasons why hydrogen today is super expensive, largely because it gets trucked to those fueling stations. The most cost-effective way to transport hydrogen is via a dedicated hydrogen pipeline. And so that is what SoCalGas is actively investing and studying today. And so we have a proposal to build what would be hopefully the largest clean renewable hydrogen pipeline system that would deliver reliable hydrogen to the LA basin to power the ports, to support the heavy duty transportation sector. And it could also, and with providing that fuel to power these sectors of the economy, we could hopefully see a significant improvement in air quality and reduce our GHG emissions from the hard to electrify sectors in the LA region. We're about a year and a half into the process since the commission authorized SoCalGas to proceed with this work. So we're expecting to complete this first phase of Angeles Link. I wanted to highlight quickly what SoCalGas is actively doing today in terms of a tangible project with hydrogen. So we have built what we're calling the Hydrogen Innovation Experience at our Energy Resource Center in Downey. It's a showcase of how both the gas, as in hydrogen, and the electric and the renewables just kind of all come together to work and power. Essentially, it's a small scale microgrid demonstration project that we have connected to a home. So we have solar panels on site that power the electrolyzer. That electrolyzer produces hydrogen on site. Hydrogen is widely used today. There's about 1,600 miles of dedicated hydrogen pipeline. Right now we're in the process of hopefully bringing this hydrogen blending project into the real world environment. A lot of research today shows that we're pretty safe to blend hydrogen at low levels, but as a prudent operator of the gas system, right, we want to make sure that we collect actual data. And so what we proposed with the commission are two projects, one with the city of Orange Cove, and then we also have a project at UC Irvine. Why we need an injection standard today is, right, we want to be able to have a place where we can put the hydrogen that is being produced interstate. We've been in the energy delivery space for over 150 years, and SoCalGas does have a really great workforce to leverage, right? Our bread and butter is pipelines today. And so the only difference of what would change in how we operate is instead of delivering natural gas today, hopefully we'll be delivering hydrogen to our customers in the future.
And the other concern, or the other advantage about hydrogen too, is that because it's so much lighter than air, if there is a leak, it's going to disperse much more quickly than like a liquid fuel at the gas station where it can pool. And because it pools, that poses a high risk of combustion. So my opinion is that hydrogen can be safe with the right measures. But a big concern is leaks, right? Because hydrogen, it's very small. And so there are concerns about it leaking from our natural gas system. In the literature, NRAL, the Gas Technology Institute, everyone agrees that hydrogen has these properties that suggest it should leak much, much faster. But this is based upon the assumption that we're looking at flows through typical channels. Literature just suggests that up to about I've seen like 10 to 20%, you can use existing natural gas appliances with hydrogen mixtures. So these were the results. So you can see along the y-axis, it's the pressure, and then along the x-axis, it's the time. And you can see that first of all, our system was leaking, right? Because if our system wasn't leaking, the natural gas pressure should have been the same over the course of the week. So when we looked more closely at where the leaks were happening, we realized that they were happening at the joints, right? So at the elbows, at the T connections, if there were any caps or any kinds of like valves, it was happening in those areas. So then we actually spoke with some people from SoCalGas that were running experiments on 5% hydrogen blends, and they also found very similar behavior where the 5% blend was showing the same rate of leakage as just the pure natural gas blend. Classical fluid mechanics assumes that the flow is steady, that it would fall under these flow regimes that are pretty ideal, like laminar flow, that we can ignore density fluctuations, that we can ignore any changes in viscosity, and also we can ignore that the behavior of the molecules at the wall boundary. One of the key assumptions too in these macroscopic big flows is that you ignore that the flow is made up of actual small particles. But really, when a leak happens, it's not that your entire gas leaks all at once, right? You have like tiny molecules that find their way and they separate from the bulk gas and enter that wall, that little crack in the wall. And so we propose the two-step mechanism. So the first step is that you have molecules freely moving around, right? Like the air in this room, it's just kind of moving and bouncing everywhere. So first of all, these molecules have to enter the leak crack. Step two, it's that the pressure is what's driving the leak rate. And so that is why this is our hypothesis for why methane and hydrogen leak at the same rate under these kinds of conditions. And so these were some of the conclusions, so that hydrogen and methane may leak at the same rate from low pressure natural gas infrastructure. Odorants and natural gas, they're not sufficient to detect small leaks. In the atmospheric science community, there's a big concern about the short-term climate impacts of hydrogen. But because we don't have quantitative evidence that actually understands how much hydrogen could potentially leak from the system, these models are only as accurate as the assumptions that they are based on.